Welcome, Algebra 2 students, to function operations. In your purple book, this will be in Chapter 7. In your online book, it'll be in Chapter 6. Let's start right off with just kind of a definition of what exactly we're talking about with function operations. And here we have the four basic function operations, and they are the same as the four operations just in mathematics. So addition, we can add two functions together. Subtraction, we can subtract one from the other. As usual with addition, addition is commutative, subtraction is not. Multiplications, we multiply the two together, again commutative, and division, where we divide the two functions, and of course g of x cannot equal 0. So what you do here is you have your two functions, and you perform whatever operation you're asked to perform. You simplify it down by combining like terms or multiplying something out. You might use FOIL. You might have to factor in the case of a quotient, and you simplify it all the way down as far as you can. And then you also are often asked to provide the domain of the combined function or the composition of the functions. So let's try a couple. Okay, so f of x, we're going to let f of x equal 4x plus 7, and g of x is the square root of x plus x. We're going to find f plus g and f minus g, and then we're going to state their domains. So let's start with f plus g. So we first want to take the two functions and we're going to add them. So f plus g of x, which is one way to write it, would be, we're going to write f of x, 4x plus 7 plus g of x, which is square root of x plus x. And we're going to combine like terms and have 5x plus the square root of x plus 7. And this is f plus g of x. And when we state the domain of that, well, the only stipulation we're going to have on that is inside this radical sign. So the domain of that, because it includes the square root of x, is x, must switch to pen, x is greater than or equal to 0. Because you can't have a negative in that radical sign. Now let's do f minus g of x. Alright, so as we said, this is not commutative subtraction, so we have to put f of x first. And we're going to subtract g of x, which we're going to put in parentheses to avoid a sign mistake. So we're subtracting the whole thing, so we're subtracting each term. So 4x plus 7 minus the square root of x minus x. So that's 3x. And let's fix that. Minus square root of x plus 7. And as before, because we can't have the negative in the radical, x is greater than or equal to 0. So that's adding and subtracting two functions. Let's try multiplying and dividing. Okay. F of x is x squared minus 9, and g of x is x plus 3. We're going to do f times g of x, which is x squared minus 9, the quantity x squared minus 9, times the quantity x plus 3. And we're going to FOIL that, so we're going to start off with x to the third power plus 3x squared minus 9x, and then minus 27. And that's as simple as we can make that. Now this is a cubic function, and that means that if I was to sketch briefly what it would look like is somehow on this coordinate plane, it's going to look something like this. And that indeed does give me a situation where the domain is going to be all real numbers. All right, let's find the quotient, f over g of x. Well, that's going to be x squared minus 9 over x plus 3. And you can immediately notice, well, that's a difference of squares up there, or you should notice. That's a difference of squares, so I can factor it. And that means that this x plus 3 here is going to cancel with this one underneath. And we're left with the quantity x minus 3 as our answer for f divided by g, or the quotient of f and g of x. We have to make one little stipulation on this one little rule. X cannot equal, at any point in this quotient, negative 3. Because right over here, if I put that negative 3 in there, I get a 0 in the denominator. So the domain, this time, for x is all x such that x is not equal to negative 3. Next we have composite functions. The composition of function g with function f is written as g with this little circle, so g dot f, and it's defined as g of f of x. And what we're doing is taking the f of x function and plugging it into the g of x function. This is kind of like an algorithm. An algorithm is a mathematical procedure where you put an input in and you get an output, and then you take that output and you put it into you put it in as a different input, and you get a different output. And so what we're doing with this is we're going to be taking a value and putting it into f of x. And then we're going to take the answer that we get from that, and we're going to plug it into g of x. And that's a composite function, plugging one function into the next. Now you can write it where you're actually just plugging the entire function in and simplifying, and you can also evaluate. So here you see we'll evaluate, so if we have g of f of x, we evaluate the inside first, the f of x first, and then plug that in as the input for the g of x. Function composition is not commutative because you're not always going to have them equal, f of g of x and g of f of x. So when you plug one function in for the other, it's not always going to come out equal. This will get easier as we do some practice problems here. So let's go ahead and try some. Alrighty, so f of x is going to represent, or in this case, we're going to use f of x as x minus 5, and g of x is going to be x squared. They want us to find g of f of x, or in this case, g of f of negative 3. So what we're going to do is we're going to start off by evaluating f of negative 3 first, and then taking that and finding g of that. So f of negative 3 is negative 3 minus 5, or negative 8. And that's what we're going to plug in to g of x. Okay, or I guess I shouldn't use my blue. So g of negative 8, which is negative 8 squared, which is 64. So we apply the f of x first, and then we take that answer and apply the g of x function. Well, what is this good for, this composite function stuff? Well, I would say that one place where you're going to see some good applications of the composite functions is going to be in finance. And this little example here is about using coupons on your pizza, which is great because making pizza cheaper is definitely a good thing in my book. But anyway, if you were thinking of something along the lines of credit derivatives, if you think about the financial world, when you're in the investment world, there are all kinds of algorithmic math, all kinds of derivatives, all kinds of different equations that describe how much money you're going to make or how much money you're trying to make. And this is the sort of math that you probably would apply in those circumstances. So let's look at a problem, just a sweet little problem about pizza. You have a coupon for $5 off any large pizza. You also get a 10% discount on any pizza if you show your student ID. How much more would you pay for a large pizza if the cashier applies the coupon first? Okay, so what we're going to do is we're going to let x represent the cost of a large pizza. Cost of a large pizza. And we're going to write two functions. We have the coupon function and we have the discount function. The coupon function is $5 off, so that's x minus 5. The discount function is whatever we would be paying for the pizza. Now, if you save 10%, 10% discount, you save 10%, then you're paying 90%. So there you have the two functions that we would need. And what we want to do is we want to figure out what would happen if you apply the coupon first. Okay, so the coupon first would be coupon c of x inside d of x. Well, if you apply the coupon second, it would look like this. And how would the two be different? Well, on this top one, you would be plugging in the c of x function here into the d of x function. So you'd have 0.9 times the quantity x minus 5. When you distribute, that becomes 9/10 x minus 4.5. All right, if you do it the other way, you're plugging in d of x in the x position minus 5, and so that's 0.9x minus 5. And so what you should notice here is that if you apply the discount first and the coupon second, you're taking off 50 cents more than if you apply the coupon first and the discount second. So now you know how to save more on your pizza, but that's an example where you might use composite functions. Last two slides are practice, so let's jump in and let's try some. Okay, copy down the f of x and the g of x. I want you to go through and do the problems. I'm going to go through and do the problems as well in a moment. So you pause it and try them out. All right, I'm going to pause it and write them out, and you'll have your solutions. Bam, there you have it. So when we're subtracting or adding, make sure that you think about the rules for that. Like right here, I have to distribute this minus. Over here on number 2, I had to multiply the 2 together, and notice 2 and 5 exactly the same thing. Give you exactly the same thing because it is commutative. But 3 and 6, not the same. You can see the difference between the two, and notice that I had to give the stipulation for what x cannot equal. All right, last slide coming right up. All right, f of g of x, g of f of x, f of g of, and all kinds of stuff going on. Pause it, try it, and then start it back up again and see how you did. Okay, going to go ahead and do it myself. Okay, well here's the first 5, but I couldn't quite fit them all, so I'll have to add one more slide and do them out. So let's go through these real quick. F of g of 0, so you plug the 0 into the g of x first, then the answer into the f of x, and you can see here what I did is I put 3 times 0 plus 1, that's g of x, and then I went ahead and squared the answer. So you see there. Okay, f of g of 2, same idea. F of g of 23, same idea, big number answer. F of g of 5, same idea. G of f, on the other hand, we're going to square the x value first and then plug that into the 3 times x plus 1. And this one happens to also come out to 1, just like number 7. All right, one more slide of problems. Okay, going to go ahead and do 12. Oops, look at that, I forgot to fix the numbering. Hold on. Okay, sorry, I know that I screwed that up. Okay, anyway, so let's go ahead and try 12 through 15. And boom, there you go, 12 through 15. All right, g of f of 1. So plug in the 1 into f of x, and then that into g of x, get 4. Now, if we just say g of f of or f of g of x, that's going to be just leaving the x in there and simplifying it out to what you would get if you find the composition of those two functions. So I could actually go back to the previous slide, and I could take this expression and every one of the problems that was g of f of whatever number, I could plug it into this, and I should get the same answer. Same thing with f of g of x, if I go back and I work on any of those. And also for this last one, you can plug a function into itself. That reminds me of a good Vi-Heart video for those of you who might be interested. It was called Fractal Fractions. But anyway, that's it for composite functions. Next time it'll be inverses. Remember, we have a quiz next class on the stuff from the previous video. And if you have any questions, post them on Edmodo. See you in class.